Hi, everyone. I'm Jiawen Liu from University of California, Merced. In this talk, I will introduce our recent work, Sparta, a high-performance framework for arbitrary order element-wise sparse tensor contraction on heterogeneous memory systems. This work is supervised by Jia at PNNL and William and Mary, Professor Dongli at UC Merced, and Roberto at PNNL. Sparse tensor contraction has been widely used in quantum chemistry, quantum physics, deep learning, and so on. Optimizing the performance of sparse tensor contraction has the fundamental impacts in the industry and the academia. Everyone knows the natural generalization of a matrix times a vector or matrix times a matrix. Here is an example that a matrix times a vector. It's very easy to extend the notion from matrix product to tensor contraction. Here is an example of a tensor contraction. We have a three-order tensor and a vector performing the K-mode product. The idea is exactly the same compared to the previous matrix product, and it's straightforward. Here is an example of sparse tensor contraction. There are non-zero elements in sparse tensor contraction, and the elements are stored in the sparse tensor format. However, how to efficiently compute sparse tensor contraction has three challenges. The first challenge is that the size and the non-zero pattern of the output tensor are unknown before the computation. In this example, a square refers to the index and a round rectangle refers to the value. We have input x and y, which are four-order tensors. We perform two-mode tensor contraction, which are I3, I4 in x, J1, J2 in y, notated as contraction mode C. The tensor contraction generates an output tensor J, which is a four-order tensor containing I1, I2 from X, and J3, J4 from Y, notated as free modes F. As we see here, the number of non-zero in the output tensor J is 1. However, if indices of value in X or Y change, the size and non-zero pattern of the output tensor also change, though the size of the input tensors X and Y remain the same. Currently, the size of output tensor J becomes to 4. It means that the size and non-zero pattern of the output tensor are unknown before the computation. The second challenge is that irregular memory access along with multidimensional index search to the second input tensor and accumulator introduce performance problems. In this example, irregular memory access caused the severe performance problem of the spatial and temporal locality. The third challenge is that a large number of memory consumption caused by large input-output intermediate data makes significant pressure on the traditional DRAM-based machine. For example, Sparse tensor contraction can easily consume hundreds of gigabytes of memory. The memory performance and capacity become the bottleneck. To address the above challenges, we built Sparta. Sparta is a high-performance framework for sparse tensor contraction on heterogeneous memory. Sparta addresses multidimensional challenges by hash table-based solutions. It also addresses the irregular memory access issues by dynamic allocation, permutation, sortings, combining with efficient static data management solutions. Sparta achieves 28 to 576 times the speedup over state-of-the-art sparse tensor contraction and up to 98% performance improvement over the state-of-the-art heterogeneous memory approaches. Sparse accumulator, or SPA, is a popular approach in sparse matrix multiplication, which uses a sparse representation to hold the indices and non-zero values of the current active matrix law to do accumulation. We first extend sparse matrix SPA to support an arbitrary order sparse tensor contraction. This approach includes 5 stages. The first stage is input processing, in which the inputs X and Y are permuted or sorted. The purpose of the input processing stage is to address the challenges of irregular memory access. The design performs permutation and sorting on input tensors before the computation. So the design significantly improves temporal locality of non-zeros in the first input tensor and the spatial locality of the non-zeros in the second input tensor. The second stage is index search, which searches the corresponding contraction mode indices in the second tensor based on the contraction mode indices in the first tensor. The third stage is the accumulation, in which we use a sparse accumulator to store and accumulate the intermediate results. Our sparse accumulator introduces a thread-private dynamic object to store the output tensor from each thread to achieve efficient parallelism. The fourth stage is the write-back stage, in which we write intermediate results from the sparse accumulator to the output tensor J with dynamic allocation. Combined with the accumulation stage, these 2 stages address the challenge of a known size and a non-zero pattern of the output tensor. The last stage is output sorting, which is optional. Though this approach is efficient, we observe that the index search and accumulation stages dominate the total execution time. In this case, more than 99% of the time is spending on index search and accumulation stages, which are still the bottleneck. A new challenge comes up. Is the sparse accumulator approach already efficient enough for multidimensional sparse tensor contraction? The answer is not yet. To address this challenge, we propose hash table-based approaches based on a large number representation for the second tensor and accumulator to fundamentally address the challenge of multidimensional search in sparse tensor contraction. In the input processing stage, Sparta does not permute or sort the second input tensor y as the previous approach does. Instead, Sparta converts the second tensor to the hash table-based representation. In the index search stage, we first convert the contraction mode in the first tensor to the unique key, and then search the corresponding value in the second tensor hash table, namely HTY. In the accumulation stage, instead of using the dynamic arrays as the previous approach does, we also employed the hash table-based representation for this sparse accumulator. We then use the free modes stored in the Y hash table to be the key to search the corresponding intermediate results in the hash table accumulator. Finally, we write the intermediate result in the hash table accumulator back to the output tensor. The hash table-based solutions solve multidimensional challenges in sparse tensor contraction. In the challenge 3, we know that sparse tensor contraction can easily consume hundreds of gigabytes of memory. The memory performance and capacity become the bottleneck. To address this bottleneck, we employ the emerging persistent memory-based heterogeneous memory system. We call it HM. The HM system includes 2 types of memories, which is fast memory with DRAM and slow memory with Intel Optane Persistent Memory Module. We call it PIM. DRAM and PIM share the same memory controller and byte addressable due to the features of comparable latency, higher capacity, and lower cost compared to DRAM. PIM has been widely used in academia and industry. However, the big challenge is how to efficiently employ sparse tensor contraction on heterogeneous memory systems. Currently, there are some solutions. The first natural solution is to deploy the whole computation on DRAM. We call it DRAM only. This approach can achieve the optimal performance. However, this approach has a big problem in which the computation is easy, out of memory, and the program crashes. The second natural approach is to deploy the whole computation on PIM, namely PIM only. However, this approach is too slow. The hardware and software-based dynamic migrations are the most popular and the state-of-the-art solutions. The hardware-based dynamic data migration is managed by the chips inside the memory controller and is decided by Intel. The software-based dynamic migration approach is managed by the execution runtime, and this approach was published in SPLOPS 2019. However, the hardware and software-based dynamic migration solutions cannot work well in some scenarios because they cause severely unnecessary data movement. To motivate our solution of data placement on heterogeneous memory, this figure shows the performance after placing a major data object in PIM while leaving others in the DRAM. The x-axis shows the data object placed in PIM. Or in DRAM means all data objects are placed in DRAM. The y-axis refers to the total execution time. We observe that there is significant performance difference if data objects are placed in either DRAM or PIM. In this example, the memory consumption of Y and HTY is similar, but placing HTY in PIM and others in DRAM has significant performance loss compared to Y. We analyzed the memory access patterns associated with data objects in 5 stages and conclude the following important observations. First, read and write can achieve significant performance difference. Second, sequential and random access have large performance difference. Third, data objects with specific memory access patterns are not sensitive to DRAM or PIM. Based on our observations, we introduced the following designs. First, based on the observation 3, we consistently place 2 data input to the PIM. They are not sensitive to PIM or DRAM due to their memory access patterns. For the rest of the 4 data objects, we decide their placement in DRAM following this priority. This placement order is based on the memory access patterns and the access frequency. To implement the above data placement strategy, we developed some analytical models to estimate the memory consumption of different data objects to decide whether they should be placed into DRAM or PIM. In the evaluation, we employed Intel Optane DC PIM server configured with Intel Xeon Go CPU, 96 GB DDR4, and 768 GB Intel Optane DIMMs per socket. We also test Sparta on a general Linux server on Chameleon Cloud configured with Intel Xeon Go CPU and 96 GB DDR4 per socket. The input tensors are from FLOPS dataset and WCAM and iTensor. We compare the performance of Sparta to Sparse Tensor Contraction with Sparse Accumulator, iTensor, IAL, Intel Optane Memory Mode, DRAM only, and Optane only. In this figure, we observe that compared to the state-of-the-art approach, Sparta brings 28 to 576 times the speedup for different scenarios and cases. We have 2 takeaway messages here. First, has table-based solutions based on a large number of representation can fundamentally address the challenge of multidimensional problem in sparse tensor contraction. Second, dynamic allocation, permutation, and sorting can address the problem of unknown output tensor and also significantly improve the temporal and spatial locality. This experiment shows that Sparta achieves 7.1 times speedup on average compared to iTensor. The takeaway message here is that element-wise sparse tensor contraction can easily beat block-wise sparse tensor contraction, even on denser data and low fast dense gem usage. The experiment on thread scalability shows that Sparta achieves around 10 times speedup on different modes using 12 threads, which shows the strong scalability of Sparta. With our proposed algorithm and memory heterogeneity aware data management, Sparta brings extra performance improvement on the heterogeneous memory with DRAM and PIM over a state-of-the-art software-based data management solution, a hardware-based data management solution, and PIM only by up to 98%, 28%, and 65% representatively. Our takeaway message here is that static data placement on Optane-based heterogeneous memory systems can outperform dynamic data placement, which is not explored previously. Compared with domain knowledge and the workload characterization, employing the static data placement can have opportunity to significantly beat the state-of-the-art and hardware and software-based dynamic data migration. We hope our observations can inspire and boost other algorithm and application design. In short, Sparta is the first high-performance element-wise and parallel sparse tensor contraction framework for arbitrary order sparse tensor contraction. It introduced hash table-based solutions to fundamentally solve the multidimensionality challenges. It also addresses the unknown output tensor challenge and irregular memory access problem by customized dynamic allocation, permutation, and sorting. Finally, it employs static data placement combined with analytical modeling of memory consumption, workload characterization, and avoidance of unnecessary data movement to significantly boost the performance on heterogeneous memory. The evaluation shows that Sparta brings 28 to 576 times the speedup over the sparse tensor contraction with sparse accumulator and achieves extra up to 98% performance improvement over state-of-the-art heterogeneous memory solutions. Sparta is open source, and you can download Sparta from GitHub. Thank you.